Muted.
Good morning, everyone, and welcome to the webinar, A Simple Approach of Using NIR for Real-Time Process Analysis. My name is Karen Whitman, and I'll be the moderator for today's webinar. Before we can begin the presentation, I do have a few housekeeping items to go over. The webinar is recorded and will be available in 1 to 2 days. Questions will be answered at the end of the presentation portion. Any questions in the queue that are not answered during the presentation, Anthony or Dr. Sang will follow up with after the webinar. When questions do arise, go ahead and enter them into the queue by clicking on the questions section of the GoToWebinar panel and simply typing your question in. It is now my pleasure to give you a quick background on today's presenters. Dr. Chang-Wei Sang and Anthony Lai. Dr. Sang, founder and Chief Technical Officer of Eurofins QTA. Dr. Sang has more than 30 years of experience in spectroscopy technology. He has been the pivotal point in the implementation of NIR technology worldwide at Cognis Corporation. Rooted in his vision to deliver robust and highly rugged NIR systems, he invented several patents on method development, sampling systems, and QTA concept. This knowledge is the cornerstone of QTA's success on the delivery of promises of inferred analysis. He developed methods for biodiesel technology, or biodiesel industry are accepted as the AOCS K9209 official methods and alternative ASTM methods. Dr. Sang has profound knowledge and experience in dealing with the most challenging NIR applications in numerous industries and has developed thousands of algorithms. Dr. Sang is also a regular contributor to book chapters and journals. Dr. Sang received his PhD in analytical chemistry with a major in spectroscopy and chemometrics from Florida State University. Now on to our second presenter, Anthony Lai. Anthony Lai is the Solutions Manager. Anthony specializes in delivering instrumentation solutions and is a veteran in implementing customized inferred solutions for both NIR and NIR benchtop and NIR inline testing systems. Anthony has implemented solutions at customer production sites with tremendous field experience. Anthony holds a bachelor's in management, economics, and communications from Hiram College. It is now my pleasure to give the floor to Dr. Sang and Anthony.
Thank you very much for the introductions. I'd like to just start by kind of going over some of the information that we hope to pass on to you today, some of the questions that we are going to answer for you, and some of the general points of education that we'd like to share with you on this presentation, on this webinar. Some of those being who we are, a little bit in more detail, who we are and what we do. Some information on NIR analysis, the value that NIR holds, along with the value in taking NIR analysis in line, which is specific to what we're going to be talking to today. We're going to go over some of the components of an inline NIR system. We're going to talk a little bit about the challenges of NIR and how those get more complex when you take that inline. And we'll talk a little bit about the implementation process and the challenges in implementing the systems. And we'll finish up with how QTA can help, some of the services that we've developed, and how we would like to work with you if an inline system is something that you're interested in. So QTA stands for Quality Trait Analysis, and we are a unique service organization that specializes in the development, implementation, and maintenance of quality testing solutions. Our goal is to provide our customers with a fast, easy, and accurate method of quantitative analysis utilizing IR and NIR technology to meet the demand for rapid, real-time quality data. QTA is part of the Eurofins global network of laboratories and service providers. Eurofins consists of over 200 labs in 38 different countries around the world. With over 16,000 employees, we've developed competency centers in a wide range of industries, such as food, feed, grain and seed, pharmaceuticals, specialty chemicals, biofuels, agroscience, and genomics. At QTA, we leverage decades of technical experience in IR and NIR to make sure our customers are making fully informed decisions and implementing the right system for their needs. We provide a full application analysis, which includes feasibility studies and a technology review to make sure the right instrument and sample presentation are being employed. We provide all of the model development along with the critical task of ongoing model maintenance and validation. The QTA interface makes our systems equally fast and easy to use for lab technicians who are looking for a rapid analysis method, or a plant operator who needs real-time data but have little to no laboratory experience. So what is NIR analysis? NIR is one form of infrared spectroscopy. Infrared spectroscopy utilizes light from the infrared region of the electromagnetic spectrum to scan a sample, capture a spectrum, and ultimately determine a wide range of chemical and molecular characteristics about that material. IR and NIR are widely used for qualitative work with the simple comparison of a sample spectrum to a database of collected reference spectrum. Quantitative IR spectroscopy utilizes chemometric algorithms to analyze the sample spectrum that is collected and calculate results for a wide range of parameters, components, or characteristics for a given material matrix. NIR and mid-IR spectroscopy are very similar in concept. However, they use a signal from two different areas of the infrared region of the electromagnetic spectrum. Mid-IR can provide IR spectra with a very high resolution and spectral characteristics. However, the sample is required to be homogeneous, since the sample penetration is generally in the single-digit micron scale. NIR has a much deeper sample penetration with a higher absorbance, which allows for a wider range of sample conditions, including liquids, solids, and slurries that contain material in both phases. So why is NIR valuable for process analysis? There are a large number of practical advantages to utilizing NIR analysis. Once the models are developed, the test method is extremely fast and requires no preparation of the sample. It is a non-destructive test and requires no other consumables or reagents that you would need to keep in stock. For these reasons, IR is a great solution in the lab to reduce the workload on other primary method instruments like GC and HPLC. It also helps to reduce variability in other primary methods, such as titrations, since IR and NIR significantly reduce the opportunity for operator influence. A single test cycle can provide results for multiple parameters at the same time, eliminating the need to conduct a series of tests utilizing a variety of methods and instrumentation. This also contributes to the significant reduction in sample turnaround time for a full slate of tests on a given sample. NIR instruments are rugged and can be placed in the lab, a control room, or potentially out in a production area where the data is needed to quickly make production decisions, such as determining process completion or making other adjustments in real time. This aspect of IR helps to reduce off-spec production and expensive rework of finished material by rapidly providing the data you need to make critical production decisions during the reaction or production process. So why is inline NIR valuable? In addition, NIR analysis is capable of utilizing fiber optic probes that can be installed in a variety of locations throughout the plant. NIR fiber optic probes come in a variety of configurations and are rugged enough to endure high temperature, high pressure environments. This makes it possible to achieve true real-time analysis of inline material without the need to pull samples. This can help to reduce operator exposure in potentially hazardous environments and potential changes to a volatile material from the time the sample is pulled to when it is tested. In addition, the increased immediacy of the data provides the opportunity to reduce batch times, increase total yield, minimize the risk of sample contamination, reduce loss or change due to volatile components, and further reduce waste and material needing to be reworked. In many cases, the results from your inline NIR system can be exported directly into a LIMS or production information system, making it even faster and easier for plant operators to ensure that their production variables are all in the optimal range. With QTA, this data is not only available to operators or lab technicians on site, but can be accessed in real time by production, quality, and plant managers from their offices, which may be in other areas of the plant or not on site at all. QTA provides secure user login credentials to authorized users for access to our reports portal, so the data is available to anyone who needs it as soon as they need it. So what does an inline NIR system consist of? An inline NIR system consists of three main components. The first and most obvious is the NIR spectrometer with fiber optic capabilities. The second would be a set of fiber optic cables that run to and from the instrument and probe. The third component, being the probe itself, would be installed in the plant or production area. The NIR instrument provides our signal, our detector, and the ability to interface with a single or multiple fiber optic probes. Oftentimes, the plant environment can be a difficult place for instrumentation due to temperature fluctuation, humidity, and dust. We recommend that the spectrometer be placed in a control room where the environment is somewhat controlled and less harmful than the plant. Some spectrometers have the ability to interface with multiple fiber optic probes. For example, the Bruker Matrix F is a built-in multiplexer that can accommodate up to 6 probes at once. If you have interest in more than 6 fiber optic probes, there is the option of an external multiplexer, some of which can accommodate 10 to 16 fiber optic probes. In a multi-probe inline system, the cost of each additional probe is in the time that it takes to complete a cycle through all the active probes. If each test cycle is 1 minute long and you have 6 probes running continuously, the best resolution you could achieve on each trend line would be 1 data point every 6 minutes. For most applications, this is not a cause for concern. However, in processes that have a short but rapid reaction period, the frequency of the data points could be critical. The fiber optic cable can be run out from the control room through conduit to the desired location for analysis. While the NIR light can easily travel through the glass threads of the cables, there is still some energy loss along the way. A 0 to 50 meter range is the optimal range for the fiber optic cable length to preserve the signal strength. However, there are situations where that range can be extended to 100 meters. Much of this depends on the parameters being analyzed and the characteristics of the material being tested. If the trait being tested requires the analysis of very fine spectral features, or if the material is dark or has a concentration of solids in suspension, the 50-meter maximum cable length may need to be observed. Fiber optic cables come shielded in a polymer coating or a more rugged steel jacket. Either way, we always recommend running these cables through a protective conduit to keep them safe. The fiber optic probes give us the ability to scan the material in line without having to pull a sample. They come in a variety of shapes, sizes, and configurations. However, the three main categories are the flow cell, the insertion probe, and the sensor head. The flow cell is great for transparent liquids with low viscosity. A bypass is created, and the two fibers that extend from the source and back to the detector can be positioned in the cell with the proper path length. Understanding the proper path length is a vital aspect of the probe selection and ordering. The path length too thin could cause difficulties with free-floating solids getting trapped or unable to be scanned. This would produce spectra that were not representative of the material flowing past. A path length too large could produce spectra that are oversaturated or that contain too much noise, which would deteriorate the quality of the spectra. Utilizing variable path length test probes, QTA will make sure that the optimal path length is utilized in the feasibility study. The insertion probes are large, rugged probes that are capable of handling high temperatures, high pressures, and high flow rate conditions. They're single-bodied probes which eliminate unnecessary points of failure. They are normally fabricated out of stainless steel. However, other materials are available in the event of highly corrosive or extreme pH environments. Insertion probes are often accompanied or installed into gate valves, which allow for the extraction of the probe for cleaning without interrupting the flow of material in the pipe. The sensor head is a versatile type of probe that is great for food and feed applications working with solids. The sensor heads can come with a 3mm to 8mm sapphire window depending on the needs of the application. They can be fastened directly to a viewing window at a collection area, the side of a tank, or a holding bin. A no-touch configuration can also be included with the sensor head. This configuration includes a signal amplification component and allows for the sensor head to be installed over conveyor belts or transportation pipes. On this slide, we can see the top left image showing the face of the sensor, the top right image showing how the sensor head can be installed using a viewing window on the outside of a vessel, and the bottom image giving us some perspective on the size of the sensor head, along with an example of an installation in an open transportation pipe in a grain application. Here is an example of how an inline NIR system is being used in a biodiesel facility through a very simple graphic. Here you can see the red lines represent the fiber optic cables. They are being run out from the inline spectrometer to various points in the plant where the probes would be installed and inline analysis desired. In this practical example, the plant operators would be able to monitor the quality of the feedstock being introduced to the system, the progress of the reaction, both before and after each reactor, the traits of the finished product, the byproducts, and the recovered inputs. In this case, that would be the recovered methanol. And here's a list of the menu of parameters we've developed methods for inline biodiesel applications using inline NIR. It's easy to see how the use of IR here would help plant operators optimize their efficiency and ensure that their process is running smoothly. So what are the challenges of NIR and inline NIR? There are challenges and hurdles that must be overcome in order to successfully implement and maintain a NIR system. One of the initial and most difficult challenges is simply determining if an inline NIR system is going to work for your application. Investigating this solution often requires investing a significant amount of capital funds upfront for the purchase of an instrument and hardware without having any hard, observable evidence of the performance or knowledge that you're selecting the best hardware for the application. Outside of having the hardware and instrumentation you need, model development is the most technically challenging aspect and becomes increasingly more complex when you take the point of analysis inline. Model development for benchtop systems allows for a stable, repetitive environment with a controlled sample. Your variables are reasonably constant, and you have more favorable conditions for capturing your spectrum. Inline model development introduces additional areas of complexity because you must account for factors in the changing conditions and moving material. Temperature variation throughout a reaction, pressure fluctuations, flow rate, and turbulence must all be treated for in the models. In addition, anytime there is a significant change to the raw materials or process variables, the models must be adjusted to treat for these new factors, which ultimately have an effect on the spectra. These are exactly the types of hurdles that QTA's services are designed to help you overcome. We have instrumentation and test probes that would allow us to provide real performance data in the form of an application analysis and feasibility report. Before making an investment in the instrumentation or hardware, you would have tangible evidence not only that the system will work, but that it will work for your specifications. Model development and maintenance is at the heart of the service we provide to our customers. The models are just as, if not more important than the instrument and hardware used to collect the spectrum. Oftentimes, instrument manufacturers will provide initial starter models populated with a basic sample set. Oftentimes, this is good enough to get a system running, but rarely is it sufficient to provide accurate results over time. These models then require a significant amount of additional development in order to have robust models that you can rely on. QTA manages the entire process to ensure that whatever decision the customer makes, they were fully informed, had sufficient performance data to draw a conclusion, and had the opportunity to do so without an investment or capital purchase. So what is the QTA implementation process? We start with an application assessment, and that consists of a feasibility study and a technology review. The feasibility study is an opportunity for us to show our customers and potential QTA customers how our models will perform using real production samples. In order to do so, we request 30 to 60 samples with primary data. The samples will be scanned and spectra captured on an instrument provided by QTA. Feasibility studies will be performed using different types of instruments, spectral ranges, if applicable. In the technology review, the feasibility studies that will be reviewed with the client, and the technology combinations with the best performance will be recommended to the customer. Before any capital investment is made, you will have performance studies run across multiple hardware and technology options. This initial phase of the process helps the customer make well-informed decisions for their organization. Purchase of hardware and on-site evaluation. The on-site evaluation gives both parties the opportunity to take a detailed look at where the instrument will be installed and where the physical probes will be located. We ensure that the probes that were ordered are accessible for extraction and cleaning, along with proper protection of the fiber optic cables. This helps to protect your investment, but it also helps us in the long-term support of your system. With the instrument, fiber optic cables, and probes in place, we continue to fine-tune the models using sample scans taken with the actual components of the system installed. This allows us to capture and treat for additional factors that exist in line. Our validation process compares the results from the QTA models in comparison to primary data for a validation sample set. These would be samples that do not currently exist in the models, but are representative of normal production material under production conditions and scanned using the actual inline hardware. The completion of the implementation, performance modeling, and maintenance. Upon completion of the model validation, the implementation is finalized by finishing the customer preferences in the QTA user interface, finishing any automated reporting features such as interfacing with a LIMS or production information system, and issuing authorized user accounts for access to the reports portal where all of your test results are available. From there, the ongoing support takes over. QTA services include daily spectrometer performance monitoring by reviewing the spectra and the diagnostic information. This allows us to determine when preventative maintenance should be performed. It reduces downtime and provides the opportunity to have replacement parts on site and available for service rather than reacting in the event of a failure. If there is a process change or the addition of a new raw material supplier, we perform any necessary modeling work to the existing models as part of the QTA services at no additional charge. If a QTA instrument is included in the service agreement, we fully support our instruments with replacement parts and repair at no additional cost to the customer. If there is an electrical failure with the instrument that would require in-depth diagnostic, we simply send a replacement instrument next day, providing you with the maximum level of support for your inline analysis system. If you're interested in more information on how QTA can help assess an inline NIR system for your plant or facility, please contact us. That concludes the introduction to inline NIR systems. And at this time, I'd like to hand the mic back for moderation of the Q&A session.
Thank you, Anthony and Dr. Singh, for your wonderful insight on using NIR for real-time process analysis. We are just about to start questions, so everyone in the audience, if you have any questions, please go ahead and put those in the queue right now. We do have a couple questions here to start off with right now. The first one being, how can you help with my existing inline system or inline needs? Where do I start?
Well, you know, one thing that is important to keep in mind is that QTA is not an instrument manufacturer. We are not an exclusive service provider to any of the manufacturers, so we can work with a lot of different instrumentation platforms. We oftentimes can take advantage of existing hardware that you may already have in place. If there's an interest in seeing if QTA can manage or QTA services on an existing hardware platform, please do get in touch with us. We'd love to talk to you about what you have in place now, what you're analyzing, what the material is, what the parameters are, and look at providing you with an applications analysis and looking at the hardware technology that you have in place, and also how our models that we implement would perform for you.
Great. The next question is, what critical factors could fail in the inline system?
I'm sorry, could you repeat that again?
What critical factors could fail in the inline system?
Oh, okay.
Oh, yeah.
Yeah, actually, this is Qing. Anthony is the presenter, and I'm here to answer the technical questions. For this one, for inline, we know it's very different from the kind of offline analysis. For the inline, there are a lot of the complicated factors, just like the material is not really prepared, and it's a real material inside. So the matrix can be very different. It can be just like for a reaction, you have lots of the mixture, you may have a catalyst inside, you have high pressure, you have the high temperature, you may have bubbles, you may have lots of the turbulence. Those are factors that need to be considered during the modeling. So if you don't have experienced person to do this, then it will become a problem when you start the work and the instrument vendor tell you it's working and you purchase the instrument and do that. It works at the beginning, but in the future, if you have any condition change or parameter change, then you got a problem.
And I think to kind of specifically address points of failure, if the question is geared towards the instrumentation or the hardware, you know, the NIR instruments themselves have you know, what could be considered consumable parts, such as, you know, the light sources, the lasers, the desiccant that sits inside. Those would be things that would need to be replaced either as they fail or on a preventative schedule, so that the instrument never really goes hard down, other than when you schedule it to be hard down. The fiber optic cables are probably most at risk during installation. Once they are in their protective conduit and run without being bent or the fibers inside being cracked, assuming that they aren't exposed to unnecessary high levels of heat, where the insulation and the you know, the terminal ends of the fibers could be melted or burned, they should be fairly stable and well protected. Obviously, probably the most at-risk piece of the inline components would be the probes, whether they're flow cell, insertion probes, or the sensor head type of probe. Now, as I mentioned before, the insertion probes are rugged, stainless steel, single-bodied probes. Short of an extremely corrosive environment where the correct material was not selected for the body of that probe, you know, it would really take serious physical collision to cause a failure in the probe. They are designed to, you know, withstand a high temperature, high pressure environments, so they are very rugged. The flow cells, while they do require a bypass, so some additional engineering, they're fairly simple in terms of being a collar with the fiber optic ends being introduced at a specific distance to one another, end to end. They're generally very easy to clean since they are in a bypass, and they oftentimes have a flush port built right into the body of the cell. It makes it pretty easy to clean those. I would say, you know, solids being put through that aren't supposed to be there, or undue high temperature that isn't expected, are probably the things that will be most risky for the fiber optic ends that are extended into the material. From the sensor heads, you know, from the smaller pictures in the presentation, it may be hard to tell exactly how large they are, but they are pretty big and substantial. However, just like anything else, over time, as they're you know, submerged in a moving solid material, they are subject to wear and tear, just like anything else. So I would say, from a physical standpoint, the probes are probably the most susceptible to damage. However, if installed correctly, those risks can definitely be managed. And other than that, probably the biggest component would be the actual IR instrument itself. The source and the laser inside would probably be the two that we'd need to watch in order to keep uptime high and eliminate unscheduled downtime.
Yeah, so as Anthony described and what I described, there's a lot of complicated situation. It can be from the hardware, it can be from the model itself, but that's why QTA provide a total solution which help diagnose what's the problem and find out the answer and to resolve the issues.
Okay, thank you very much for that insight. Our next question is, what industries can NIR inline be utilized in?
Yeah, that's a tough question to answer succinctly. The applications are so broad in terms of industries that we can use NIR and inline NIR. I think the biggest factor that would help define what would be a good fit and not a good fit is whether it's an organic material or not. Whether it has absorbance and we can see it from an IR perspective. Liquids, solids, slurries, they're all capable of being analyzed. The variable there is the type of sample presentation hardware that we use, and also the type of IR signal that we use, whether that's a mid-IR, a near-IR, or FT. All depends on the type of material and the specific parameters that you'd be looking for. We have clients and customers that are in everything from biofuels, specialty chemical, food, animal feed, seed and grain, to crop protection. So polymers, monomers, very, very wide range of applications. But the best way I can answer that question is if there's any interest in looking at it, give us a call. Feasibility studies are at no cost, so it is definitely in your best interest to kind of be fully educated, fully informed on it if there's any interest.
Thank you. Our next question is, any limits on how far the installment sites of probes in the IR machine?
I think I'll let Ching tackle this one, but I think what the question is there a limit on the distance between the instrument and the probe installation?
Oh, okay. Yeah, just like for this question, Anthony already described in his presentation. Actually, if somebody can use it up to 500 meters, but it's special case, only as he described, all kind of the pathogens, you also have energy, non-pathogens, all kind of the fiber optics lens has energy loss also. So if you are detecting very minor component, less than 1% or something, or less than at a point something percentage, that kind of the information, if you go through a long distance, then it's hard to detect. So we normally suggest within the 50 meter. And some, if it's really in the very long distance, then we'll suggest you have build another closure around your reactor and use the electronic cable to connect to the control room. So, but the user doesn't have to worry about it because we'll evaluate and we'll look up their environment and decide what kind of approach will be the best to save the money and also the safe way to get good information.
Yeah, and I think that's where the value of the on-site evaluation really kind of comes into play, because we can look and see what options are available to us. Obviously, with the instrumentation and the hardware, there's going to be different options available based on the technology that's being implemented. hardware that's being implemented, types of probes, etc. But it'll give us an option to look and see if, like Ching said, if an enclosure is going to be the best, and actually putting the system out in the middle of the plant in a protective enclosure, or it could be that 2 separate instruments might be a better solution. But it allows us to kind of review all of that with the customer, with the plant personnel and quality personnel, and really understand what the best solution is going to be for them.
Thank you. The next question that we have, and as of right now our last question for today, is how long does a complementary feasibility study take to complete?
Okay. Yep. So the feasibility studies, really one of the main factors in terms of the duration of time it takes to complete one is the ability to collect the proper samples for the feasibility sample set. So one of the things to keep in mind is that when we request 20, 30, 40, 60 samples throughout the feasibility, it's not necessarily to say we would like 20 of the exact same sample. What we really need in order to give you the information that you're looking for is samples that represent the full range, pushing the limits of the range that you would expect to see at a given test point. That range is really what will allow us to have everything that we need in terms of samples and data to give you some performance indicators of how well this is going to work for each given parameter that you'd like to test for. If we got 20 samples that are all right on top of one another, all we're really telling you is that we're able to identify a given number that's static, where what we want to be able to do is show you how well it can predict values across a range, and when that gets outside of the range that you're comfortable with or that you're expecting to see. So that's probably the biggest time factor, is the collection of those samples over the range. Outside of that, once we get those samples and have an opportunity to work with them, the samples and the data, we're generally looking between a week to 2 weeks to turn around a full feasibility report. So given that, generally feasibilities that kind of begin and close within a 1 month to 30 to a 45-day span.
Yeah, we normally provide the customer a spreadsheet, and the customer will fill in what kind of material they want to analyze and what kind of the trait and the concentration range and what the primary method and what the condition. From there, we would work with the potential customer about the next step, what kind of sample we need, and the possible concentration range or the kind of possible variety. So we include those kind of variety, and we do a kind of feasibility study. That one is the key point. Before we do anything, we need to have a feasibility study.
Okay, thank you. We actually had a couple more questions come in during the answer. One of them is, does QTA's inline system require an internet connection? If so, what if I don't always have good internet connection in my plant?
That's a great question. The QTA systems, looking at a benchtop system, the standard QTA platform is internet-based. It is that way to ensure that you have real-time analysis using the most up-to-date models available for the material that you're testing. That does become, in all honesty, a point that we need to look at when we take a system in line. So what we've done is created a solution for that called QLink. And what QLink is, it keeps your IR system online via the internet, However, in the event of the loss of internet connection, the Q-Link box, which is essentially a black box that operates between the instrument and the computer that you're using to interface with the instrument, and it basically captures all of your latest models as they are when internet connection is lost. The black box then serves as an intermediate QTA server right then and there. So there's literally, with the loss of internet connection, there is zero interruption of your service. This becomes critical when you're talking about inline production environment testing, where now all of a sudden the data coming out of the QTA inline system is how you determine when to move your material out of a reactor into good holding, or determine, when to begin a stripping phase or to pull vacuum. Losing that data then all of a sudden becomes a major hurdle. So the Q-Link black box solution that we have in place resolves that so that you don't lose your data. It captures all of the latest configurations and models. And then as soon as internet connection is restored, the black box then syncs everything back to the QTA server so that all of your data, all of your results that were captured in that time where you lost internet connection get synced back and are available through the reports portal, available in the local database on the computer, and you're running seamlessly.
Okay, thank you. And our last question for today is, actually, we have two more again. My next question is, what is the main difference? There's many different consultants and vendors. What are the main differences between them in QTA or between consultants and vendors?
Sure. I would say the easy way to answer that question is that a consultant kind of comes in when there's an issue, when you notice some variation between your results coming out of your spectroscopy, your IR instrumentation and your primary method. QTA is there every day. QTA supports, provides support 24/7, whether that's instrumentation questions, errors you may be receiving, or questions about the results. I mentioned in the presentation that we do daily diagnostics to make sure that we are aware and understanding the condition of the instrument, being able to have replacement parts on site, such as light sources or lasers when they need to be replaced. For kind of hitting that off beforehand. A consultant really doesn't do that. They're going to update a model and give it to you, and that's the model that you use for now between the next time you call them. It's kind of a point of need type of a request, where QTA is your partner in your IR analysis system. We support you 24/7, and anything that happens that you need to have happen with the models, that's included in your service, and we take care of it immediately. James, did you have anything to add to that?
The other difference is just like for the instrument vendor, you need to buy your instrument first, and normally their purpose is to sell your instrument. We have seen a lot of these kind of case, and also they purchase the instrument because our instrument vendor told them it's working, and it's working at the beginning, but there's a lot of complexity, and once it will not work, when they start to do it by themselves, it becomes a paperweight over there because they scared to use it. So they already invested money, it's big loss for the customer. But QTA is different. We provide the service rather than instrument, selling our instrument. So we need to make sure it works. If it doesn't work, then we cannot make any money. So we really need to make sure it works. That's a guarantee for the instrument performance, for the model performance, for your result. So that's the difference. we are providing a service. We are not selling you an instrument or just give you a kind of one-time consultant. It's different.
Okay, thank you. The next question is, will I have to go through our IT department to have the software installed? And what should we do when the network computer is down for reboot or updates?
Yeah, in regards to, I'll try and answer this question the best, to the best of my understanding of what information they're trying to get to. But there is software that needs to be installed. I did reference the QTA user interface software. We would absolutely work with an internal IT group to make sure that the software is installed properly, the correct permissions have been granted, to make sure that the online services aren't going to be blocked by a firewall. So yes, we would absolutely work with work with an internal IT group to do that. So in terms of a computer going down for an update, an internal update, we can certainly work out some different solutions. We do have clients who have 2 computers, up and running and installed with QTA software, so that if one goes down, they have another to swap in. If there's an internet issue, related issue, again, QLink may serve to be a really solid solution. If a network issue is persistent, or if a firewall or permissions issue persists, the QLink box may be a real solid solution to get around some of those IT hurdles.
Okay, thank you, Anthony and Dr. Tseng. We don't have any more questions for today, so I guess that concludes our question and answers for today's webinar. Thank you again, Anthony and Dr. Tseng, for all of your wonderful insight. And thank you to our audience for tuning in today and listening to our webinar. I hope everyone's had a great morning, and we'll have a great afternoon. Thanks again, everyone.
Thank you.
Thank you.